For more information, please visit SGMAK Associates website.
Let's talk about test of hypothesis. Rejecting the null hypothesis is always a strong conclusion, since the decision maker knows how often a correct hypothesis is rejected. If we set up the probability of type 1 error, alpha, at 5%, then we are prepared to reject a correct hypothesis 5% of the time and take correct decision, which is accept hypothesis that is true 95% of the time. However, failing to reject null hypothesis can be a weak conclusion unless we know that the associated probability of type 2 error, represented by beta, is small. Because of this, the statement about which a strong conclusion is desired appears in the alternate hypothesis. Once again, the statement about which a strong conclusion is desired appears in the alternate. A two-sided hypothesis is appropriate when we are interested to maintain a process parameter on a target, and we are interested to detect any deviation from the target. The problem statement should provide strong indication towards setting up a two-sided alternate hypothesis. Many hypothesis testing problems involve a one-sided alternate hypothesis. For example, if you are trying to improve process yield, we want to make strong conclusion only when the true mean is larger than mu naught. In this case, we set up the hypothesis as null will set as mu equal mu naught and alternate as mu greater than mu naught. The following approach should be taken if there is doubt as to how to set up the one-sided alternate hypothesis, whether you set up the alternate hypothesis as less than type or greater than type. Let us use the following examples. We need plastic containers that must withstand more than 150 psi of internal pressure for a specific application. The decision maker has the following two choices. Set up null as mu equal mu naught and alternate mu is greater than mu naught, or null always as mu equal mu naught and alternate mu less than mu naught. So the question is, which one is the correct choice? In this example, the container is unsafe for use if it fails to withstand more than 150 psi of internal pressure. Let us consider the first choice. If we reject the null hypothesis, given it is true, then we are accepting unsafe containers for use. Because null true implies that the containers cannot withstand more than 150 psi. However, if we make type 1 error, we decide in favor of the alternate hypothesis and accept unsafe product for use. Now let's look at the second choice. The null hypothesis implies that the containers are good. The type 1 error implies that you reject good containers as unsafe. Now if you compare the severity of type 1 error in the two choices available, we can conclude that the first formulation captures more serious error as type 1 error. We must agree that accepting unsafe product has more severe impact compared to rejecting good products. The recommendation is to accept the formulation that captures the more serious error as type 1 error as the correct choice. Once again, the recommendation is to accept the formulation that captures the more serious error as type 1 error as the correct choice. In this case, the formulation null mu equals mu naught and alternate mu greater than mu naught is the correct choice. Remember that the decision taken by rejecting the null hypothesis is always a strong decision. In case of one-sided hypothesis, of the two choices available, the formulation that captures the more serious error as the type 1 error is the. Let's look at an example. The tensile strength of a fabric should not be less than 160 psi. Based on prior experience, the process standard deviation is 5 psi. A random sample of 5 yields an average of 162 psi. We get X bar sample average of 162 psi based on a sample of size 5. Test the hypothesis at 5% level of significance. Based on the reason provided earlier, the correct formulation should be null mu equals mu naught and alternate mu greater than mu naught. It's the correct choice. Intuitively, we reject the null hypothesis. It's a two-sided. It's a one-sided test. Intuitively, we reject the null hypothesis if sample average is larger compared to what is expected if null hypothesis is true. In this case, the decision rule is as follows. We'll be rejecting null hypothesis if X bar sample average is greater than mu naught plus z 0.05, because we are testing it at 5% level of significance, multiplied by sigma over square root of n, or X bar is greater than 160 plus 1.645 multiplied by 5 over square root of 5, or X bar greater than 163.68. So if you get a sample average greater than 163.68, it's too large a value, it's not consistent with null, and we reject the null hypothesis. In this case, sample average based on the experiment is 162, so we fail to reject the null hypothesis because it's less than 163.68. Our decision is not to reject the null hypothesis. We state that the data collected support the null at the specified level of significance, or there's not enough support to reject the null hypothesis at that level of significance. This test shows that the fabric does not meet the strength requirement. Once again, the rejection region for null hypothesis is derived based on the requirement that the probability of rejecting the null is true is 0.05, which is our type 1 error. And it is an upper tail test. Null hypothesis true implies that the X bar follows a normal distribution with a mean of 160 and a standard deviation of 5 divided by square root of 5. For a lower tail test, we set up null as mu equals mu naught and alternate mu less than mu naught. The decision rule is we reject the null hypothesis if X bar is less than mu naught minus z 0.05 sigma over square root of n. A low value for X bar, sample average, compared to the expected behavior if the null is true, leads to rejection of the null hypothesis. And the rejection region determines how low is still consistent with the null hypothesis. This analysis is based on normality assumption for the random.
For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website. For more information, please visit SGMAK Associates website.